So hi everyone, thanks Dorian and Toby for the introduction and for inviting me here to share our research. So I work in this area called human-robot interaction. For those who don't know, it's this really exciting field that tries to bring human beings and robots together. So there's this growing recognition that HRI is important because of some of the larger trends we see. As you know, robots are moving out of their confined factories to human field environments, and they're also expected to do more. They're expected to handle unstructured environments and learn from mistakes. And as Toby was saying, I got my start in this area when I was a PhD student at Yanis Demir's lab, where Toby also was from. And over there, I worked on smart wheelchairs for children with disabilities, helping them get around safely. So fast forward to today, and I'm kind of still working on how to make humans and robots play well together. So my students and I spend a lot of time asking questions about how to make robots that interact fluently with people to improve their lives. So HRI can be rather broad as an area. So we like to focus on specific scenarios, such as the one that I'm showing on the screen. So here you see a nurse helping to clean a patient's wound. And the question is, can a robot participate in this sort of interaction? Can a robot do what the nurse is doing? And if not, why? What's missing? Is it that we haven't quite put the pieces together in the right way yet? Maybe some jigsaw puzzle, but we kind of haven't figured out all the pieces are there, but we haven't really figured out how to put them together. Or are we lacking some of the pieces? Are we, do we not have some key technology or scientific insight to make this happen? So for this particular scenario, I think there are a number of key challenges to address. I think actually some of the pieces might be missing. And I want to talk about two of them. There are many, but I'll talk about two of them. And one is that simply to perform well, I think the robot needs a good sense of touch, tactile perception, essentially. It needs to apply the right amount of pressure to clean the wound, but not cause harm or too much pain to the patient. Second, I think there's an issue of trust. So while this picture makes it seem like it's static, so the patient doesn't seem somewhat passive in this scenario, she's not passive, right? If you put yourself in her shoes, it takes a great deal of effort to hold your hand out when there's a cut and someone's kind of prodding it, right? It's painful. The thing you want to do is pull it away. You replace that nurse with a robot, and I tell you that if I was in her shoes, I'm not letting that robot anywhere close to my hand. All right. So there needs to be this element of trust that a robot is there to help and help in a good way. And my talk will center around these two issues and some of the progress we've made in these directions. And while I'm talking about this specific scenario, I'm kind of interested in general methods that solve a class of problems. So problems like this, right? Not just this specific one. So before I start delving into details, I really want to, do a shout out to my postdocs and graduate students and undergraduate students and research assistants. I'm really fortunate to work with really brilliant people. And it's really their work I'm sharing with you today. So thank you to all of them. I would also like to thank my collaborators, Desmond, David, Benjamin. They're not pictured here, unfortunately, because there's no space. But one day I hope to get a picture of all of us together, post-COVID, when that happens. I'd also like to thank the NUS School of Computing and the Smart Systems Institute, which I'm part of, as well as my funding agency for supporting my work. So my group, as Dorian mentioned before, we're called CLEAR, or the Collaborative Learning and Adaptive Robots Lab. We're more of what we call a technical advances lab in the HRI parlance. That means that our focus is on developing new methods, new algorithms, new systems for HRI. But most of our tools, most of our tools are in machine learning and decision making, as what Dorian mentioned before. But we also run user studies, so to validate our models, to get inspiration for new methods, and such as the one you see the video on the screen here. So one thing my students learned very early on is that running user studies is crucial. Very often participants don't act or react in the way you expect them to. And maybe one reason for this is that as roboticists, we have a very precise set of skills and background knowledge, which shapes the way we perceive things, the way we think, and the way we act. We can differ from the average person that you meet. And we'll talk a little bit about this in a moment. So today, I'll focus on conveying some of the, our key high-level ideas and findings. And for details, we can pull up in Q&A, and I'll also point you to relevant papers as we go. And you can find out more on the website that's shown on the screen. So let me start with trust today, and then we'll move on to touch. But what is trust? I think we seem to understand it at the common sense level, and this word is used a lot, and then the semantics gets a bit overloaded. Actually, in general use as well as in academia. So trust has been studied in many different fields. disciplines in the social sciences, the psychology, economics, neuroscience, philosophy. So the definitions for trust actually vary widely depending on the field. Without going too much into formalization at this point, I think this picture kind of summarizes our intuition of what trust can be. So I'm not sure whether you participate in one of these trust activities, but the person on the raised platform essentially has to fall backwards and hope his friends catch him. And I would invite you to imagine this scenario where you replace this person's friends with robots. If you would you trust your robot to catch you? I don't know, the robots in my lab aren't really built for that. So the answer for me will be no, but depending on the robots you have, you may say yes. So trust can be seen as kind of a willingness to put yourself at risk with respect to another agent. Okay, and we're going to focus on trust in robot capabilities of performance rather than intent. I'll talk a little bit about intent towards the end of this of the first part. So why do you care? Why should you care about trust? Because bad stuff happens when you don't consider it. I mean, take for example, the Handover disaster that happened back in 1923. 7 US Navy ships ran aground because the captain didn't trust the ship's navigation aid and just ignored its bearings. Fast forward to today, and we have the opposite problem. People seem to be over trusting their self-driving cars and not supervising the systems appropriately. And we know about the unfortunate accidents that can happen as a result. So my collaborators and I have been working on trust. Let me start with this paper we published back in 2017. A group of us, David, Sid, Stefanos, and myself, worked on this paper, putting trust into planning. And let me kind of explain the setup here. There's on the picture on the left, you see a table clearing setup task, where the robot here is kind of capable of removing all these items. So it's tasked to kind of pick up the items and put it on the tray. But the human being doesn't know that the robot is fully capable of doing this task. Okay, so the robot does something like go straight for the fragile, expensive object like the glass cup. The human being may intervene. In fact, we do see participants do this because they, it's just like when my 5-year-old tries to pick up, a piece of expensive china. He wants to help us to, bring it to the kitchen, to the sink. But I stop him right away because I'm afraid that he breaks it, right? And that's not desirable because here, in this task, the robot is fully capable of doing this, but and the human being intervening is just getting in the way. But if the robot is kind of able to model trust and incorporate that into a POMDP, well, then it starts to do something interesting. It starts to build up the human being's trust. So first, it goes for the plastic bottles in green here, and then which are cheap and doesn't matter if you drop them. And then maybe the can, which is in red here, and then finally it goes for the glass cup when it infers that the human being's trust may be high. So incorporating trust into decision-making, what it does is it reduces this intervention rate, okay? And I really like this work, but one of the questions that it came up, it left me a little bit puzzled. I mean, why did it work? So as roboticists, you know that when you program a robot to pick up a plastic bottle, it doesn't mean that they can pick up a glass cup or a screwdriver or anything else for that matter, right? There's a lot of work that goes into general grasping and pick and place that tries to solve this problem for arbitrary objects. And I notice that there's some work here at QUT as well, but it's an unsolved problem. So what I think is going on is that our participants in this experiment and lay people in general aren't burdened with this background knowledge, and they generalize what they observe using common sense. And I want to find out more about this phenomena because if we understood it well, maybe we could infer when human beings may have inappropriate levels of trust because they're over or under generalizing. And in this scenario, for example, does the human trust in the robot extend to tasks that have nothing to do with picking and placing objects when he sees the robot performing this task? So the big question is this, how do human trust in robots transfer or generalize across different tasks that the robot may be doing? And this study led to a paper that was in RSS in 2018. There's a longer, better version of it that came out in IJR in 2020. And the key conceptual insight is that we should model trust not as a unidimensional element, that's what we were doing in the POMDP work, but really as a multidimensional entity to take account different kinds of contexts, such as the type of task. We'll see that really what the human being is doing is some sort of functional learning, and I'll share a little bit more about what I mean by that in the upcoming slides. So to study this phenomenon of trust transfer, we first performed an in-lab HRI experiment in 2 separate domains, each with 12 different tasks. So in the household domain, which is a fact robot, this fact robot over here, and whether they would pick up and place different kind of objects or navigate to the room under different circumstances, sometimes with objects in the scene, sometimes totally clear or to a particular area. In the autonomous driving domain, I'm not rich, so I don't have my own self-driving car. So we use a VR simulation of one. we kind of hooked up this Oculus Rift to participants, and then they would observe the self-driving car performing different kinds of driving and sort of parking maneuvers. Now, the two domains are separate. There are no crossover tasks because, well, the robots are different. But kind of using these two domains helps us to ensure that whatever we discover about trust, it just isn't just specific to one of these domains. So participants would come into our lab, and we would get them to organize the 12 tasks by their type and perceived difficulty. And then we would ask them, how much they trust the robot to complete 3 different tasks. And then they would observe the robot performing 2 of the tasks, where the robot would either succeed or fail at both tasks. And then we would ask them again, hey, how much do you trust the robot to perform 3 of the tasks that we asked you before? And we wanted to kind of see what the change was. So what did we learn? So there's some graphs here, but let me just give you the major highlights due to time. So first finding, if we trust the robot to perform a particular task, say picking up an apple, we are more likely to trust the robot to perform something similar, say picking up a cup, compared to something very different, say navigating to the dining room. Second, trust changes are shared. So when we see a robot performing a task, it doesn't just change our trust in the robot's ability to do that one specific thing, but also in tasks that the human being didn't see the robot do, so unseen tasks. And finally, trust transfer is asymmetric in a way. So when you trust the robot to do a certain task, it's more likely that you trust the robot to do something you perceive as easier compared to something that's a lot more difficult. So those findings are very intuitive. It kind of gels with what we expect when we work with people, right? How we trust them. But now can we take those findings and translate that into a computational model of trust so that our robot can start to reason about this phenomenon? So in our lab, we think about trust as a latent variable that influences the human being's actions. So for example, in this graphical model, the human being's initial trust is formed by the context, some initial context, as well as personality traits. So some people are just more trusting than others. And it changes as they interact with the robot. So we need to specify 2 things: how trust is represented, essentially this circle over here, and what are these dynamics, how it changes the observations. So in the earlier trust form DP work, we modeled trust as a simple real number with linear Gaussian dynamics. But now we're going to generalize that to be a function over a space. Okay, and what kind of space? It's going to be a kind of psychological task space, all right, which defines how similar tasks are. So in this work, we use vector task spaces. Each task is represented as a real vector in some perceptual space Z. And we learn a projection function over here that takes some observed task features. They can be whatever you like, but in our case, we use census descriptions of the task, and we map it to some point in the task space using some learned parameters. Okay. Depending on the task features, of course, you're going to get a different point in the latent task space. And here, where the 12 tasks in our household domain end up, you can see they're clustered. There's a pick and place task over here and the indoor navigation task over here. Now, given this space, we can model a person's trust in an agent at any given time t. So trust in an agent at any given time t as a function over these real vectors. Okay. And then we can ask the model, hey, what is Toby's trust in the robot's ability to navigate while following a person? All right. And the model says 0.64, which means that Toby isn't quite so sure. But trust is not static, as I mentioned before. It changes according to observations of robot performance. So we can model this to be an update function. We call that G. All right, and that takes in the observations and it updates trust. So if Toby were to see the robot start doing some fancy navigation, this trend changes his trust, so that now his assessment of whether the robot is able to follow a person is increased to about 90%. So similarly, Toby may currently trust the robot to pick and place a lemon, but after seeing the robot kind of fail really badly at picking up this apple, he no longer trusts the robot to do so. And you can see that that's dropped significantly there. All right, so in our paper, we described 2 different models under this general kind of scheme. Both models make use of a learned task space. However, the neural model is kind of a deterministic approach which measures task similarities using dot products, and the Gaussian process, the GP model, arises from viewing trust as a form of Bayesian function learning. So the key difference is really in the kind of flexibility of the trust updates. So the neural model is purely data driven. It uses this gated recurrent units, or GRUs, to learn how to update trust. In contrast, the GP model assumes that people are Bayesian in nature. Our brains combine prior notions of robot capabilities with the evidence that we see of robot performance via Bayes' rule. So for those of you who are familiar with GPs, here's a little bit of extra. You know that when people use GPs, the mean function is typically 0 because we don't care about that so much. You can put in a bias. Here we're going to put in a bias because we are interested in incorporating some initial bias about to model the human being's prior experience. So you could do this, like I said before, we had the mean function, but you can also incorporate pseudo observations, right? That's another way to do it. Which can the parameters for these can be trained alongside the rest of the model. So regardless of what you pick at the end of the day, whether it's neural or Bayesian model, our computational experiments show that taking into account trust transfer leads to better predictions. So our model is more accurate compared to techniques that just trust uniformly across the tasks, such as the linear Gaussian model, when predicting trust scores for held up participants. In the household domain, the pseudo observation GP, this one performed a little bit better, but in the driving domain, the RNN worked better. So we see similar results on a second experiment where instead of holding out participants, we held out the task. Okay, this is more difficult, but again, the models perform well. The learned projections, this kind of indicates the learned projection was capable of generalizing beyond the training task. So a natural question is, we had this, the RNN and the Bayesian model, can we combine them in some way? And the answer is yes, you can. And it leads to even better performance. And you can find this in the IJR paper. But in essence, I think what's going on is that the Bayesian model is providing some sort of inductive bias. So people are doing some sort of learning, but it may not be completely Bayesian in nature. So the neural networks allows for them deviation from that. So to summarize, I'll be going a little quickly, but to summarize, the key idea in this work really is just to formalize trust dynamics as function learning over this kind of learned task space. And the approach is by no means limited to just task structure. So we can extend this approach to capture, how trust differs or transfers between different robots, as well as different kind of environmental conditions. But that's kind of future work. If you want to learn more about work in trust, you can head to our website. You'll find Yachi's work on intent as well as capabilities, trust and intention as well as capabilities. There's a survey paper from Bing Chai, and then also some work on trust calibration, where the robot is teaching the human being about its own capabilities while simultaneously learning about human intent and abilities as well. So now let's move on to part 2, which is on tactile or touch perception. So our skin is an amazing organ. Okay, it's our sense of touch allows us to explore the world and interact safely with our environment and as well as other agents. And human beings have skin too. I would say that the technology behind them is you can get cameras everywhere, but robot skin is less available. But I hope there will be someday. So they're not as scalable as the skin that we have. There's a biotech that's been around for some time. It's a multimodal sensor, amazing sensor I've used in our lab. More recently, these optical tactile sensors such as Gel Slide and Gel Sim have been gaining popularity because they generate tactile images that you can pass to like a deep net, and you can do your classification and learning, all that jazz. Today I'll discuss an event tactile sensor we're proposing called the New Touch. So the New Touch is a biologically inspired tactile sensor. It's about the size of your fingertip. Okay, it has a 3D printed bone, as well as a graphene-based pressure transducer on the top of a 39 taxel electrode and a soft EcoFlex protective layer. Okay, so I'm not a hardware guy. Let me say that up front. And we built this sensor in collaboration with Benjamin T and his postdoc at the time here. So with this New Touch sensor, your robot can start feeling pressure and forces and kind of acting based on that information. Here, the robot is going to pick up some soft tofu, which is slippery and it breaks easily. In fact, see a human being just broke tofu accidentally just a few moments before this video was shot. This is a live kind of demonstration. There were people in the room and things like that. So the robot got a firm grasp, not too light, not too hard, and it's transporting the tofu across to the plate here. So I'll talk a little bit briefly about kind of how the New Touch works and some of the machine learning that you can use in order to interpret the signals out of that. So what's special about the New Touch is that it's neuromorphic. So neuromorphic literally means brain-like, and like our brain, the New Touch is event-driven. So you probably know this, but your brain is not the GPU. So it's not doing matrix vector multiplications, millions of them every second. Rather, your neurons are processing little packets of energy called spikes. Okay, spikes go in, spikes come out, and your neurons can fire asynchronously. And it's through this kind of processing that intelligence or human intelligence emerges. So the event-driven principle here can be used to construct sensors. Here I'm going to show you kind of spikes coming up with two kinds of event sensors. The first is the event prophecy event camera here mounted on our Frankie Amica robot arm, Frankie, and the new touch event sensors, the tactile sensors here. Okay, so I'll just play the video once first, just to give you an idea what's going on. The kind of what you see that the sensors are generating will appear here. Okay, I'll explain what's going on. So here the camera is mounted, okay, on the robot, as I mentioned, looking down at this soy milk carton. So as I press play again, you're going to see the grippers come into view, right? The pixels that are changing in the environment, and then here comes the lift. All right. So unlike a standard camera, so how standard cameras work is that they capture a fixed number of frames every second, so 30 frames, 60 frames, and you get this regardless of whether there's anything happening in the scene or not. So you could be pointing the camera at a blank wall, and the camera is going to collect like 30 white blank frames every second, and that's a waste of energy, a waste of space. So event cameras work very differently, similar to neurons. You know, each of these pixels, as you saw before, fires independently and asynchronously, and the spike is only generated, you know, when the pixel intensity, you know, changes beyond some threshold. So the same principle actually applies to the tactile sensor. So I'm going to play, and you can see here where contact happens, and then here comes the lift. Right. Now, why might you be interested in event tactile sensors? So as I alluded to before, because of this event-driven nature, you only store and compute when there's some change, and often that's what you're interested in. And this can lower power consumption and increase temporal resolution. And it's because when you're not transmitting so much of the redundant information, it can also, you know, it can really improve the scalability of the solution. So, but the spikes you saw in the video are quite, you know, they're a little bit different than the images of frame-based movies that, you know, our robots kind of handle. And they are long, discrete time series. And, you know, it's a question whether we can make sense of those signals to enable robots to do useful tasks. And so that's what that's kind of what my student task were like, you know, over here, and the team tackled in our RSS paper. And the key finding here is that an event-driven framework can indeed accurately classify SIP and also identify different kind of objects. And here we are going to fuse visual event sensing as well as tactile event sensing. So our framework comprises three ingredients. The first is the sensor, which I already spoke about. The second is our learning model. And the third is the loss function to train the model. Now, in this work, we try to go all out event-driven, but caveat, okay, it's not fully event-driven. I mean, the robot runs on a Linux box, okay, with ROS, and the sensor, but the sensor and the learning model are neuromorphic in nature. Okay, in a moment, I'll show you some power improvements because of that. So let's talk about the model. So if you've seen, you know, deep learning work, which I think most people have nowadays. So if you've seen deep learning work on multimodal inputs, okay, then, you know, this should look somewhat familiar. I think we have two modality experts, you know, a vision expert, which takes in spikes from the prophecy, and a tactile expert, which takes in spikes from new touch, all right? And then that's fed to a combination layer that's passed to some task network, and that gives you some output spikes. Now, the key difference, of course, is not, it's really in the activation functions. Here, this isn't ReLU or sigmoid, it's a spiking neuron. So it uses something called spike response model. There are different kinds of spiking neurons as well, but we use a simple spike response model. The spikes come into the spiking neurons. Here, these lines are all spikes. They come in, they increase its internal energy, what we call the membrane potential. And once that exceeds a certain threshold, that generates an output spike, okay, shown here. And then the neuron goes through a refractory response. And we can train this model in various ways. We train this model using labeled data and a loss function with approximate backpropagation, okay? Now, we can't use a loss like cross entropy because here we're dealing with spike trains rather than real vector outputs, okay? So the input is going to be, you know, a bunch of spikes, right? And the output you're going to get is also a bunch of spikes. And, you know, you can't use cross entropy because, you know, there's no way for you to account for these kind of spikes. So what we're going to do is we're going to use something called the spike count loss, which has been used before, of course. The idea is very simple. So imagine if you have a neural network. Okay, oops, let me do this. And the input is here. So this is our spike train. And we have two outputs. Okay, so let's say we're doing this to classify slip. All right, so we have two output neurons. Let's call one slip, and this one is no slip. What we're going to do is we're going to specify some desired number of counts, of a desired number of count that we want. So here, for example, if the object is really slipping, we'll say, okay, I want this to fire 100 times within a specific time period. Okay, and the no-slip neuron should maybe fire 0, or maybe some low number, maybe 5 times or something like that. Okay, and now we have a desired count. We run the model, so we run some data through the model, and we see how many counts we actually get. And that's going to be our obtained count. We take the difference, square that, and you have your loss function that you can train your model on. So let's just give it a go. You take this spike count loss, you have your ingredients all there, you apply it to a SIP classification. So here there are two objects. They're visually very similar, but the object on the left is stable and the object on the right is slipping. So this video is slowed down because this happens really quickly. It happens about 1/10 of a second. So you blink your eyes and it's over. And the question is really, can we detect slip using our framework? So this plot shows the accuracy of our model versus time. So let's start looking at the modalities separately. So models trained using only one specific modality, and then we'll look at combining them. So the tactile only model performs, oops, let me do this. Okay, tactile only model performs better early on, right? But it kind of reaches a plateau. The visual model doesn't perform so well initially, but later on catches up and then starts to perform better. Now, when you combine the models shown in green here, okay, it does achieve perfect accuracy by the end, but it has a really undesirable profile. So what you would really like is that you would like for it to kind of follow this tactile expert at the beginning and then switch over to or really incorporate the visual expert's inputs later on, right? So you would like to follow this kind of profile, but you don't see that when you use the spike count loss. So what's going on? So what's going on is that there's something not quite right about this loss function. So you can see here that loss is simply based on desired counts, right? And there's nothing to tell the model when the output spike should occur. So the model could wait till near the end before generating these output spikes. So to fix this problem, Task came up with a really simple approach, okay, which was to temporarily weight spikes. You can do this in various ways, but he chose to temporarily weight spikes. And if you choose appropriate weighting function, say linear decay, then the spikes that are earlier are more heavily weighted. So if you apply this new weighted spike count loss, then you see that you get kind of the behavior that you desire, where it follows the tactile expert at the beginning, and it kind of switches on to the vision expert as the vision spikes come in. So we've also applied our model towards container and weight classification. Here are 4 different objects with differing amounts of liquid. And the task is to classify each container and weight. And the containers here are kind of opaque, so vision only doesn't quite do the work. So here, initially, the vision model performs better. And the reason for that is because as the gripper is closing, you saw before, the movements cause a little bit of movement in the arm, and hence the camera, because the camera is mounted on the arm, and it shakes, and so it reveals the object, all right? The tactile spikes don't start appearing until about 2 seconds in when contact is made, all right, like in the video. And when you combine both vision and touch together, you do get a better accuracy, but this again doesn't have quite the temporal profile that we like, right? We would prefer to kind of get a good result early on, which is good for early classification, and then kind of get better when the tactile information starts coming in. So applying our weighted spike count loss again fixes this problem. Okay, you see the kind of weighted model, combined model, sorry, tracking the visual model at the beginning and then kind of incorporating the tactile information as that comes in. So finally, thanks to Intel and my student Jethro, we were able to test our slip detection models on the Lohi chip, which is this neuromorphic chip. Okay, and we compared that implementation versus a GPU implementation, and the two models achieve similar accuracy and latency, but the neuromorphic model really requires dramatically less power, okay, compared to the GPU implementation, which is quite nice. I think in the future, if you want mobile robots, that don't consume so much power, this might be a nice solution. Okay, so now that you know more about these event-driven sensors on UTouch and how they can be used, let's look back at this scenario. You see that the nurse is not in direct contact with the cotton ball or the wound. Okay, rather she's handling it using forceps, right? So, and then she's feeling tactile sensations through the tool in order to provide proper assistance. Now, that form of inference and control using tools is really fascinating. And that's what we decided to explore in a recent paper that was published in IROS last year. And the key message is that, using fast vibrotactile perception, combining sensing as well as machine intelligence, that can reveal contact information on grasped tools. So not only the kind of point of contact, but also the material that the tool has come into contact with. And we call those extended tactile perception, since we are kind of extending the robot sensing capability beyond its body. So it's through the tool now. So you don't need to sensorize tools necessarily. If you have a tool and it's grasped appropriately, you can sense. It's as if you have virtual sensors on your tool when it comes to contact with objects, and you can sense what kind of the contact position that you'll see as well as the material. So again, we take inspiration from human beings. Human beings have this remarkable ability to do this. Okay, we do this all the time. And how this works is that when contact occurs with the tool, little vibrations are transmitted along the object, which are picked up by the mechanoreceptors in our skin. And the resulting spike patterns are interpreted by our brains to infer where and with what contact occurred. So in a similar fashion in this work, what we did was we developed an updated neuromorphic tactile sensor, the new skin, which has 40 texels and is capable of 4 kilohertz sensing. So in this example, we are localizing taps along a rod. The dynamic events are sensed by the new skins is captured, and then passed to some feature extractor. We try out different ones, and then through some learned model in order to predict the contact location. Okay, so what do we learn? So through our proposed framework, we can actually show that you can get pretty accurate localization on held rods. The error was as low as 5%. And there are detailed experimental results comparing different kinds of feature extractors, machine learning models. In the papers, if you're interested, you can take a look at that. We also go into quite a amount of detail about guidelines essentially for using vibrotactile sensing for this kind of extended perception, such as the kind of speed of sensing that you kind of require for this task, as well as the role of spatially distributed texels. I mean, the skin is that you need to sense it fairly rapidly, about 2 to 3 kilohertz for this task, and the more texels you have, the more robust your regression is going to be. So in addition to tap localization, we can also use vibrotactile sensing for more complex tasks. So here we explored 2 of them: grasp stability during robot-human handover, as well as for food identification for assisted feeding. So we can show that grasp stability prediction just using the dynamic tactile sensor, so no other modality, during robot-human handover can be performed to accuracy about 80%. I'm just going to, of course, go higher if you incorporate other modalities as well. And if you were to do food classification through a fork, and this fork is just a regular fork, we bought it from IKEA, and you can do that with surprising accuracy. I mean, the model makes, to me, very reasonable errors. I mean, it was surprising to me that it could distinguish between the empty class and water. So the empty class is just there's nothing on the plate, so it was a kind of control. And water, it was just dip the fork in water, and it was fairly distinguished the 2 cases fairly well, and I thought that for water, the forces would be too small to pick up, but it seems to do a pretty good job. There are other errors also, and those to me were fairly reasonable. I mean, apple and pepper, an apple and pepper slice of that, they have similar hardness as well as texture. So I think that's a pretty reasonable error to make. So if you want to find out more, visit the website. You'll find a few more papers on tactile related work. Here's just 3 examples. This is some early work that I did when I was a PhD student with Yanis. And we proposed one of the early models for incrementally learning by touch. More recently, one of my postdocs was looking at how we can incorporate textile geometry using graph neural networks. And my student Kai Chi is looking at how we can use vision as well as tactile feedback to do self-supervised reinforcement learning. I'm also trying to push our sensor and tactile perception system out of our lab and maybe into yours if you're interested. So my collaborator Ben T and I are working with a great team to robustify and make the whole system kind of plug and play. So fingers crossed, we're having headwinds because of this current semiconductor crunch. But if all goes well, we'll hope to have this sensors available by October this year. Maybe before that, we'll see. And if you're interested, all you have to do, go to this website, technique.ai, click subscribe, and we'll let you know when the sensors are ready. So let me kind of bring us back now to our original motivating scenario. I don't think we solved anything, but hopefully, I don't think we solved everything. But here, I hope that we made some headway on this very challenging problem. As we move forward, so I'm kind of thinking about the ways we can kind of integrate these pieces together For one, this picture doesn't really do justice to the communication happening between these two people. So the nurse is not just silently cleaning the hand there. That's kind of an odd thing, odd experience, I think. What she's doing is usually giving words of encouragement, and reassurance, trying to establish trust. And the communication can be quite nuanced and typically multimodal in nature. So it's not just speech, but also eye gaze. And you see here, she's holding the patient's hand, so it can also be via touch. And we have some work under review on how we can provide multimodal communication using rapidly learned human models. And maybe one day soon, I'll be able to share more on those results. So thank you very much. If you want to find out more, please email me. You can visit our website. You'll find write-ups of paper, code, data sets. So and I like reproducible research, so a lot of data sets available online, and you can reproduce the plots and so on and so forth. I wasn't able to share all of our work. For example, there's some stuff I really like on burst RL and sample refinement for deep general models. I really love that work, but it's not like intersecting with robotics yet. It's on the machine learning side. And of course we are hiring. So if you're looking for a position, please let me know. I'm hiring postdocs as a research assistants. Sorry for that ad, but I struggle to hire people. I'm sure you guys are experiencing that as well. And so if the stuff I present today looks cool, you're interested, please send me an email. Okay, thanks for being a great audience. Let's move to questions.
Awesome. Thank you very much, Harold, for an excellent talk. If anyone has any questions, if you'd forget to unmute your mic and raise your hand. Or I think Karma, is that hands? No, that's just the clapping. Okay. Alrighty. Searching. There's quite a few people in here.
Maybe I'll start, Harold, while we're waiting for us.
Sure.
Really, really cool work, amazing work. Thanks a lot for the presentation. It was really enlightening. With your human-robot trust works, have you looked at differences in the personality traits of different people and how that changes the dynamics over time?
So we haven't. This was raised also I was speaking to one of my colleagues over in the US, and he was asking the same question, because one of the questions we have is, what instrument do we use in order to gather data about these personality traits? And we didn't do that for that work, but we're going to have some future work coming up. I have a student coming in, and we're going to look at that question precisely. And he was recommending some of these survey instruments in order to look at the big five and stuff like that, in order to try to get at how these people differ, basically their personality traits, and then kind of figuring out whether that just affects the initial trust, or whether that affects also the dynamics of things as they see the robot do things. I'm gonna guess that yes, the answer is yes, it's gonna affect, but how much is a big question.
Yeah. Cool. Thanks, Harold. I've got a million questions about the touch perception and all the event-based stuff, but let's take it offline.
Okay, sure.
All right. I don't see any other questions so far, but I actually have a question. With the new touch stuff, what is the sort of the vision, pun intended, for the new touch? Is it just like looking at fingers? Are we looking at potentially like superhuman reflexes, that kind of stuff? What is your vision for that? Okay,
so there are a few. One is that when I was working the wheelchair stuff back with Yanis, the thing I really wanted to do was to wrap the entire wheelchair with skin. I mean, that was a thought I had at the time, and there was no technology that existed at the time that allowed me to do that in a good, reliable way. Wires would be everywhere, just a nightmare. So we didn't do that, of course. But now I think we're approaching a point where we can start to do that. And that's where I'm going to push that to scale it up, right? So that we can have tactile sensors covering the entire robot. I think that maybe skin can fill up some of the gaps that vision cannot, where vision doesn't provide. Okay, it's hard to put cameras everywhere, I think, and also maybe for privacy reasons, maybe you don't want cameras everywhere, in which case skin might be a better alternative for safety reasons and so on and so forth. We would like to have some superhuman reflexes, if you will. I think that we can already get there with some of the things that we're doing. In fact, some of the activities we're pursuing with commercializing, or rather getting these tactile sensors out, is doing on trials to see how fast we can do simple things like pick and place with delicate objects and things like that. Hopefully one day, we're not at the level of human performance yet, but we're getting close. So I think that once we get there, it'll be cool. There's nothing stopping us from technological front. So in terms of the sensor itself, it's fully capable of doing that. But I think that closing the loop, getting the whole sensing, perception, kind of control all tied up nicely in the closed loop, that's where we are working. That's what we're working on now.
Cool. Sounds like a pretty cool title in the making then, for the next generation paper. All right, we got a question from Tendai Makasi.
Like, yes, ahead. That's nice. Oh yeah. Well, thanks very much, Harold. That was quite interesting. The work that you're doing is really, really interesting. So I had a question. So looking at the model that you have here, like the human robot trust and then the touch perception. So one thing that I was just thinking of is there could also be an element of emotions that's built between maybe the patient and the nurse, and something that could also maybe relate to a robot. Like, I mean, if a robot is going to be able to express certain emotions, then it's going to have an impact on the trust. So I was wondering if you're also like sort of looking into incorporating that as well in your research or something. I mean, I'm also asking this because of sort of like the alignment of my research, which is more aligned to robots, but from an online environment. So I'm thinking of if it's going to be sort of like an online interaction with robots, there's going to be less touch, but it's going to be more emotional. So like that sort of component, are you also, I don't know, maybe trying to touch on it?
So that's a great question. Effective computation is one of the things that we're definitely looking at. So I had a FYP student who is now a PhD student. He was looking, FYP is a bachelor's thesis student, and he was looking at this question, whether if a robot shows an appropriate emotion or an inappropriate emotion, how does that affect trust? So the robot was performing some task and it would fail, and during failure it would display perhaps the wrong emotion. It'll appear happy rather than sad, all right, or just find a conflicting emotion. So there we find the results to be somewhat inconclusive at this point. So that's why I haven't published a paper on that. It seems I don't know whether it's due to the experimental design at this point, or rather maybe the effect is small. So we're looking into that at the moment. However, just my intuition tells me that yes, the emotions that the robot displays would impact how trust evolves over time. Now, I think we have to be careful when it comes to trust and kind of display of emotions. Now, I think that it's one of the things that we have to be careful of in HRI is not to deceive people, all right? And showing emotions may inadvertently lead people to believe that the robot has emotions, which is not the case. At least the robots I know today don't have emotions. And so we just have to be careful about that. So I'm still, in my mind, at least philosophically, I'm trying to kind of argue those things out for the benefits versus the kind of the risk that we take when we're having robots that display emotion. But super interesting question and super interesting area. I think effective stuff is like a really nice area to go into.
All right, thanks for that, Tendai. Next up is Ben.
Thanks, Dorian. Thanks, Harold, for the wonderful talk. My question just follows on from Dorian's question, actually, about the touch sensors. As a roboticist looking for robots that interact with the world in more interesting and exciting ways, the touch sensors look awesome. If you were to put a crystal ball on it, how long do you think we are till, especially those skin sort of sensors you were talking about, could be mainstream and readily available for robots?
So it's hard to say because I'm bad at predictions. I often make wrong ones. I mean, I made wrong predictions when during the Trump election and during Brexit, completely wrong predictions on my part. So I'm terrible at making predictions. So don't take anything that I say. I can say about the sensor that we are making. Okay, so the sensors we are making, we are hoping to get that out, this year. All right, that's the one, and it should be robust enough that you can just plug and play. So that's what we want to start using out of the box. Whether we're talking about large scale sensors, so things that maybe you can wrap a robot in, that will take longer, I think, just to make sure that the system is robust enough. So I think one of the problems that so it's not a problem necessarily, but you know how things are when we build sensors in our lab. They are prototype versions, right? So they'll work, but they'll work for a month, and then you have to fix them, and then that doesn't that's the big problem. And the tactile sensor is not like a camera where you can just put it mounted on a robot and it's just passively observing the scene. Tactile sensors, you have to grab objects, and that interaction with the world causes abrasion. It causes a wear and tear, and so you're going to replace the tactile sensors. And the tactile sensors have to be cheap enough that you can do this already. The part that comes into contact with other objects, that has to be cheap enough. So yeah, getting all these things down requires some time and effort. So I think that's going to be kind of getting the last part there is the challenge, I think. But not too long. I hope not too long. I think that one day we're going to be able to buy tactile sensors just like we buy cameras. We're just going to buy them off the shelf, and we can get them in all kinds of configurations and sizes, and we can kind of use them on our robots. At least that's what I think. How long it would take, I don't know. I don't have a precise answer for you there. Sorry.
It sounds exciting regardless. Thanks.
Okay.
All right. So we're running a little bit short on time. So just there's two more questions in the chat. One is by Jesse McGovern, and it is the goal for AI to become more trusted than their human counterparts?
That's kind of that was not my, so I don't have that intention going out. What I would like to say is I think just having more trust, I don't want people to have necessarily more trust in robots. I want people to have the right amount of trust in robots. I want trust to be calibrated. I want you to have the right mental model of robot so that you trust it in appropriate ways when you're engaging with it. So I think that the mistakes happen when you overtrust or undertrust a robot. And I think that's what I'm trying to do. I'm trying to come up with methods so that the robot can kind of tell you how much you should trust it and do it in a transparent way. So that's kind of my goal, not to necessarily make it more trusted than human beings. I think moving forward, I see a role for both human beings and robots in lots of the different kind of setups that we are envisioning.
All right, very nice. Oh, we suddenly have quite a few more questions.
Okay.
Well, yeah, we'll just do a quick one. We'll go until 12:15, so we got 3 more minutes.
Okay.
Will Brown has said, are you combining 2 strands touch for HRI, as in touch to build trust? And there's some link there.
Yes, I would love to do that. Right now, I'm just trying to work out how to get it past IRB. So we're going to have people coming in and maybe have the robot touch them and things like that. And that requires ethics approval. And we're kind of sorting out the experiment because this approval can take quite a bit of time. So we're just sorting out how to do this in the right way. I see on the chat there's a link. So I'm going to check out that paper and then we can get some inspiration from that. Oops, sorry. Let me move that back.
Actually, Harold, yeah. So let's see, there's about 1 more question from Andrew, and then we have 1 more camera question from Henry. So Andrew's question is, hi Harold, thanks for the talk. Do you think multiple touch sensors across a robot arm or via holding an instrument could be used to sense collision tissue texture and even create maps of confined workspaces like inside the body for minimally invasive surgery?
I think the answer is yes. We are working on this at the moment, actually. So touch sensors can also detect, depending on the type you use, can also detect proximity to a degree. And so you can use that to kind of have a short range sensing before contact actually happens. So yes, we can do these things. And future work, I can't talk too much about that because it's work in progress. But yes, you hit on something really, really interesting there.
Very nice. All right, we've got our last question here with Henry Fraser. If anyone else has any other questions, they can just contact Harold directly. Henry, go ahead.
Oh, thank you so much for including me. So I am not a technical person, I'm a legal background. And so the legal, trust means something very important in law and has a lot of interesting meanings. So for example, in product liability, the basis for liability is not meeting the public expectation of safety, of how safe product is. In negligence, a relationship of trust and vulnerability gives rise to duties to take care. And you mentioned calibration. How do you see the challenge of communicating the correct level of trust? Because it's illegal. It's a matter of liability for the roboticist there. How do you see that challenge?
Yeah, so that's the thing about trust. There's all these different definitions, and I'm not a lawyer, so and I'm bad with legal stuff. So we try not to view trust in that way. All we're trying to do is to get the human being essentially to have the right amount of trust in terms of their willingness to put, like I said, willingness to put themselves at risk with respect to the robot. Now, what the legal implications of that is, we haven't thought that through. I'm working with right now I'm working with a lawyer actually. He's a legal scholar over at the Singapore Management University, and he thinks very deeply about these issues. And we are kind of talking to one another to see whether we can join up these dots, the questions that you are asking, which are extremely pertinent. So we have kind of worked out how to do this, and the way he thinks about this is perhaps a little bit different from the way I do it. So I kind of view it from a more technical perspective, but he's looking at it on a societal level, right? And as well as the legal frameworks that come into play, and a more holistic view, imagining inside the process and all the little bits that go into that. And it's a challenging problem, and we're working out how you can combine these two pieces together. I don't know yet, but we are working things out. Yeah.
All right, everyone. Harold, please everyone give thanks to Harold for a very excellent seminar. And
thanks everyone.
If you have any more questions, I feel sure Harold would be happy to answer them via email or something like that. All right, and the recordings will be up when I have a chance to process them, and I'll send you the link, Harold, so you can distribute them on your side.
Okay, thank you.
All right.
Thanks a lot again, Harold.
Thanks.
Thank you.
Thank you.
Take care.
Take care.
Bye, everyone.
Bye, everybody.